what we're going to do is find the shielding factor experienced by a valence electron in chlorine. So we're not going to walk through the example of sodium, instead we're going to walk through the example of chlorine. And the usefulness here is that in walking through this example, we're going to be able to compare our shielding factor for sodium versus chlorine and compare our effective nuclear charge for sodium versus chlorine. This is going to give us a good idea for how effective nuclear charges result in differences between our atoms as we move across the periodic table horizontally. All right, so let's start with our shielding factor for the valence electron in chlorine. So I'm just going to go back and forth between our rules in this example so we can continue to see where we are. So rule number 1, we have to write out the electron configuration, and we're going to pick out the electron of interest to us. All right, so the electron configuration for chlorine, we can use the periodic table as a roadmap or a guide. In order to get to chlorine, we're going to have to pass through our 1s2, or our 1s subshell, 2 electrons in it. We're going to have to go through the 2s subshell, put 2 electrons in that. 2p, 6 electrons go there. 3s2, so 3s orbital, 2 electrons go there. And then finally we make it to the 3p subshell and 5 electrons are present here. So there is 1 electron missing, keeping it from becoming completely full. Only 5 electrons present in that 3p subshell. All right, so what does it mean to pick out, though, your electron of interest? Well, we are looking at a valence electron in chlorine, and most notably, we are going to be looking at the subshell that was the most recently filled. Since chlorine is a p block atom, meaning that it's an element that's found in the p block of the periodic table, we are going to be the most concerned with that outermost, not only valence shell, but also subshell. We're going to be paying attention to the 3p orbital and its 5 electrons. Now, if we want to calculate the shielding just for a valence electron, we're going to pick out one of these electrons to be the electron that we want to pay the most attention to. So what we're going to do is rewrite this 3p5 in another way. It's going to help us kind of pick out, again, when it comes to calculating our shielding factor, again, which electrons do we want to pay attention to, which electrons contribute to that capital S. So I'm just going to rewrite our electron configuration. Everything on the inside stays the same. 1s2, 2s2, 2p6, 3s2, and here's where the difference is going to be. We're going to pick out one of these 5 electrons. The other 4 electrons are the ones that are going to be adjacent to us. So this is us. We are here. The 3p electrons, the other 3p electrons, are those that are adjacent to us in the subshell. So we are one of them, the other 4 we're just setting aside, and they are going to contribute to the shielding factor S. All right, so rule number 1, check. We have written out our electron configuration, and we have picked out the electron of interest to us. This is one of our 3p valence electrons. Now, outer electrons shield us 0% of the time. Since there are no electrons behind us, since we are in the most valence shell and subshell, there are no electrons behind us in outer shells. So we don't really have to pay attention to this rule. We can just skip right on over it. It doesn't apply to us. All right, rule number 3 is going to be where we start calculating some stuff. So adjacent electrons in the same shell are going to shield us 35% of the time. Now the shell that we are in, our shell, is n equal to 3. Our shell is n equal to 3, which means all adjacent electrons are going to be those that have the n value in its quantum number set also being equal to 3. So rule number 3 is going to tell us then that we need to pick out all of these electrons that are adjacent to us. Not only these 3p electrons that are immediately adjacent, but also the 3s electrons, because they also have a quantum number of 3 in front of the s. So we can see that there is a total of 2 plus 4 electrons that are adjacent to us in the third shell. So there are 6 electrons total, and they block our view 35% of the time. So what we're going to do is multiply this 6 by 0.35, which is the equivalent of 35% just in decimal form. All right, we're going to put a pin in this. We are going to add up everything in kind of one fell swoop as we go. So we're going to add this to the results from our next rule. So this is check. Inner electrons that are in the n-1 shell are going to shield us 85% of the time. Well, if our current n is equal to 3, this means that the first inner shell is going to be n equal to 2, right? This is n-1. So now we have to work our way deeper into the atom. We're looking at the inner electrons in the next shell, where we can see that there are a total of 2 plus 6 equals 8 electrons that are in the n-1 shell, and we're going to see these 85% of the time. All right, we have one shell left. Just to go back, those are all of the electrons in the n-1 shell. Last but not least, we have to look in the n-2 shell, or deeper if we happen to be working in like larger atoms. All right, n-2 corresponds to our last little grouping in here. These are the deep electrons, which are going to be an n-1 in our case. We can see that there are only 2 electrons here, and each one of these 2 electrons we are going to see 100% of the time. So our total shielding factor is going to be a sum of each of these 3 cases, where the 6 electrons that are adjacent to us, again, are blocking our view 35% of the time. The electrons in the first shell in are going to be blocking our view 80% or 85% of the time, and the innermost electrons we see all the time. So our total shielding factor, which is going to be a sum of each of these things, is going to be equal to 10.9. In other words, if we are hanging out in the 3p subshell, we are going to see 10.9 other electrons at all times. There may be a total of 17 electrons inside of this atom, but we only see 10.9 of them because everything's moving around. This, right, all of the electrons in this atom are dynamic, and so we're going to see 10.9 of them at any given point in time. All right, so now that we have our shielding factor, we can use this to calculate what the effective nuclear charge that is, or the effective nuclear charge that is experienced by this electron that we're hanging out next to. Our effective nuclear charge is going to be equal to the atomic number Z for the element of chlorine, which is equal to 17. And we're going to subtract out that shielding factor that we just calculated, a total of 10.9. This gives us a grand total of 6.1, and this is equal to the, again, number of protons that are seen by the valence electron that we're hanging out with. So we see a total of 10.9 electrons, and we see a total of 6.1 protons.